Hello and welcome to Vidra Ambed channel. Today in this tutorial I am going to show you how we can balance the LEDs using MPU6050 with STM32. We are going to interface the MPU6050 with I2C and we'll take the data from the accelerometer. And we'll control the LEDs by rotating the accelerometer. So I'm going to show you how we can interface this MPU6050 with I2C, and I'm going to read only the accelerometer data for time being, but you can also try the same experiment with the gyroscope. So this is how the connection diagrams are look like with respect to the nuclear board. You can use any STM32 board. It need not to be a nuclear board. Okay. So I'm using the Nucleo G071RB. So and this is the MPU6050, which is having the 3-axis accelerometer as well as the 3-axis gyroscope. Okay, so total it is a 6-axis motion sensor from the InvenSense. You can see here if you look at the pin nodes. Okay, the first pin is the VCC pin, so we should connect to 3.3 volts, and the second pin is the ground pin that should be connected to the ground, and this third pin is the SCL. It should be connected to the PB8 of the nuclear board. So I'm basically connecting to this pin, and whereas as TA pin should be connected to the PB9. So you can use any I2C peripheral, whether it is I2C1 or I2C2, depending on your board capability. You can use any I2C interface. Okay, and then apart from the I2C, I'm going to use the 4 LEDs just for the indication. You can use any LEDs, that is not a problem. So I have taken 4 LEDs. One is blue, and the other one is red, other one is yellow, another one is green. So these LEDs are connected in diamond fashion, and all LEDs are the positive terminals are connected to respective GPIOs with the 220 ohm resistor. You can also use for 1K resistors also, not a problem. So depending upon the resistors that you use, the intensity of the LED will increase or decreases. So I have connected these 4 LEDs to 4 GPIO pins. So namely PB6, PB15, PB10 and PB13. You can use any GPIO pins. It doesn't matter which GPIO pins you are going to use. Okay, and all negative connections of the diodes, that is light emitting diodes, are connected to common ground. So all are connected to common ground, and we are going to read this accelerometer data both on x-axis, y-axis and z-axis, and we use those data from the all 3 axes, and we are going to toggle these LEDs by rotating the MPU6050. So mostly we are going to use the x-axis data and y-axis data. So that's all about the connections. So let's move on to STM32Cube IDE to create a project. Okay, I have opened the STM32Cube IDE. So let me create a new project, and here you need to provide your board or part number. I'm using STM32G071 RBT6, which is based on this nuclear board. Click on this, click on next, and then I'll give LED underscore balancing MPU 6050. Okay, of course you need to select the target language as C, executable, and the target project type is STM32Cube IDE. Click on next and click on finish to create the project. Let me go to the system core, click on sys, select the serial wire debugger and time source as a systic. So RCC, I'm going to use the internal clock oscillator. I don't have any external oscillator connected to this nuclear board. And then go to connectivity. I'm going to use the I2C 1. By default, it is selected as a PA10 and PA9. So, but we have connected to PB8 and PB9. So just hold your control and then move to PB9 and also the PA9 to PB8. So this is how you can actually relocate to the pins and then assign to them. Okay, and coming to I2C parameters, so we are going to use the standard mode only. If you want, you can also use fast mode. Okay, that's not a problem. I'm going to use only standard mode. Apart from this, we also need to select the 4 GPIO pins. Okay, so blue LED is connected to PB6, red is PB15, blue is PB6. So here it is. I'll just make it as an output, and I'm going to rename it as LED underscore blue, and PB15 as a red, Okay, 10 as a yellow, 13 as a green pin, LED underscore green. So now we have configured the I2C as well as the 4 LED pins, okay, which are connected to the board, okay. And then after that, go to clocks configuration. Of course, I'm going to use the internal clock oscillator. I'll give the maximum frequency, that is 64 megahertz. Click on enter. Okay, now the clock frequency is set to 64 megahertz. Okay, and then click on this save to generate the code. Okay, so now the code is generated. First, we will write the code for MPU6050 and read the data. So, and we will observe the MPU6050 data. Based on that, we will turn on or off the corresponding LEDs by rotating the MPU6050. So for that, I'm going to declare a type definition here. Okay. So just I'll declare one structure to hold the values of MPU6050. We are going to use the integer 16 for accelerometer raw value. I will tell you how to get this raw value. Similarly, we need to do it for AY and AZ, and we want to declare three more variables. Those are for actual values. Okay, double AY and double AZ. This is not comma, this is okay, and I'm going to give this name as MPU6050 underscore T. So what I have done is first we will read the raw values from the MPU6050, and with that raw values we are going to create the G values. Okay, I'll tell you how to calculate these G values based on the configuration that we given to MPU6050. Okay, so I'm going to write a code. Most of the code in the user code begin 0 and user code begin end 0. Okay, first I'll declare one hash define MPU6050 address LED RESS. Okay, and the MPU6050 address is the 0x68. So you can find that easily in the data sheet. So let's go to the data sheet. Okay, so this is the data sheet that I have with me. Okay, which will give you the registers of MPU6000 as well as the MPU6050. So currently we are focusing on the MPU6050. So now if we come down, you will see all the register sets. Okay, so the one which we are interested in is the who am I. Okay, and here you can see this register actually provides the data of MPU6050, and if you look at here, the default value of the register is 68. So which means that the device address of the MPU6050 is the 68. So we have taken that here. Okay, so and we are going to declare two functions. Okay, one is a void which is nothing, MPU6050 INIT initialization function. Okay, which is going to take the I2C definition. Just give the I2C1 and we are going to also declare another function read ACC raw data. Okay, which is going to take two parameters. One is the handle and the other one is the MPU6050 underscore T structure definition. Okay, this is the structure name that we have given. You can always check here. Okay, and then you can give in here MPU6050 struct. This is the name of the structure we are going to give. Okay, now so to initialize the MPU6050, so we need to look at the corresponding registers, and then based on that we need to actually send the data to the MPU6050 to initialize it. Okay, so again now go to the register here. Okay, and there are some registers which we need to consider. The one is let me go to the overview. If we go to the page 5, you will get all the registers here. Okay, the first register that we are going to see is the power control register. So this is the power control register. Okay, we have two. One is for power control management, one on management two. So we are going to use the this one, okay, which will actually reset the device first. Okay, so the address of the this register is 68. Okay, so let's go to code here. Okay, so let me declare a variable underscore t. Res is equals to 0 cross 6b. Okay, so we are going to write this to the MPU6050. So we are going to take another variable, that is the right value. So I'm going to reset the device with the zeros, and let me take 0 cross 0 0. So this is the register and this is the value that you are going to write. Okay, so let's take the hall underscore I2C underscore mem write. Okay, so we are going to use the hi2c1 device address. Okay, so device address is MPU6050, but we should shift it to 1 to make it as a 7-bit address. So mem address is the register. So mem size is 1 byte, and data that we are going to send is this one. Okay, right? So since it is a pointer, we need to pass it as a ampersand. So right value, size is 1, and I'm going to give the timeout as 100 or 1000. You can also give 1000, 1 millisecond, that is fine. Okay, so hope you understand. So we have taken the registers that we are going to write, and we have also taken the data that we are going to write. Similarly, we need to also configure a couple of more registers. Okay, and the other register is sampling rate division. Okay, if I go to this one, so let me copy this will provide the sampling rate to. So this is the sampling rate, so which is going to give the sampling rate for the gyroscope. Though we are not going to use the gyroscope, but as a part of initializations, we need to do this. Okay. Here they have given a sample rate and the gyroscope output rate divided by 1 plus sample rate division. So, and here they are only giving that the gyroscope output rate is 8 kilohertz. Okay, and we can select this register either 0 or 7. So based on that it will going to select the sample rate. So I'm going to select the sample rate to 1 kilohertz. So that is the reason why I'm going to give the sample rate value to 7. Okay, so that is what I mean by this. Okay, so let's go ahead and configure this. So the address of the register is 19. So let me copy all these things just to overwrite the values. Okay, so the address of the register is 19. Let me check again. Yeah, it is 19, and I'm going to send the value as 07. So this is going to select the gyroscope sample rate to 1 kilohertz. So you can also copy paste the formula here. Okay, so what we have done is here the sample rate is equals to 8 kilohertz divided by 1 plus 7, which is equals to 1k. And then we are going to configure the accelerometer and gyro. Okay, so let's go to the configuration registers. Again, let me go back to registers here again. Yeah, so these are the two registers that we are going to configure to set the default values. Okay, to both gyroscope as well as for the accelerometer. So first we'll set the accelerometer. Accelerometer is the 1C. Okay, so let me go to that register. Okay, here they have given something called the AFS underscore selection. This is also important for us. So this is the AFS underscore selection selects the full scale range of the accelerometer output according to the following table. So if you provide the value of value 0 to this okay, these two registers, okay, I mean these two register bits, so that will set to plus or minus 2G. If you provide 1, plus or minus 4G. If you provide 2, it will give it as a plus or minus 8G. And if you put a 3, then it will provide it as a plus or minus 6G. So we are going to configure it to plus or minus 2G only. So for that, So I'm going to reset all these values. So I'll put everything as a 0. Okay. So let's copy this. So the register is 1C, and the value that we are going to write is all zeros. Similarly, for we need to set it to accelerometer, and for accelerometer also, I think what is the register value is 1B, and of course the data that we are going to write is 0 zeros. So what we have done is we have declared one function MPU6050, and then we have taken the corresponding registers, and then we have written the default values to them. Okay, so that's all for the configuration. Now let's move on to the another function, that is MPU6050 read underscore accelerometer underscore raw data. So in this function we are going to read the data, and the value that we are going to get out of this register data is going to be a raw data. Now let's go to the accelerometer read register. Okay, these are the config registers. Yeah, here you can see. So register 3B is providing the accelerometer data. Okay, as I said, I'm going to focus only on the accelerometer. Okay, let's search here. Yeah, here it is. Okay, if you go to this page, and here you can see that the address of the starting address of the register is 3B. Okay, and if you see here from 3B to 40, they are providing data in 8 bytes, 6 bytes, sorry. Okay, so the first 2 bytes are corresponding to accelerometer X value, and the next 2 bytes are corresponding to accelerometer Y value, and the next 2 bytes are corresponding to accelerometer G values. Okay, and again you see here. Okay, so the first, it is totally 16-bit of data. That is the reason why when we declare a raw value variable, okay, so we have given it as a int 16 underscore t. Okay, which is represents the, we are going to hold the 16 bits of data. But here you can see that first we are getting the upper byte, and then the lower byte we are getting. So we need to shift this upper byte. Okay, and then we need to add it to this lower byte to get the total value of the x. Okay, and again at the bottom you see here they have written something like each 16-bit accelerometer measurement has the full scale defined accelerometer underscore fs. This we have already seen, and we have set it to 0. For each full scale setting, the accelerometer sensitivity for LSB in accelerometer underscore x underscore out is shown in the table. So that means, for example, if we get a raw value of 300 in the x direction, so and if you want to get the corresponding g value to that raw value, then you need to divide with this. Why we need to divide with this? Because we have configured the full scale range to 0. Suppose if you configure the full scale range to 1, then you need to divide the raw value with this value. Hope you understood. And of course these are the two complement values. Okay, and you can calculate and you will be able to get it. Okay, now so let's read the accelerometer values. Okay, so the register that we are going to give, so let me copy this. So the register is, what is the register, is 3B, and we are not going to write any values to this register. We are going to read the values from the register. So let me give the read values. I would say read values. So we are going to get the 6 bytes. So I'm declaring the 6. So I'm going to declare the 6 bytes. Okay. So instead of write, we are going to give the read value. So of course, and the device address is the MPU6050, and you can directly copy from here. Okay, and the mem address is this one. So let me give the range, and mem size is 1, and the data that we are going to read is this value. Since it is an array, we don't need to pass ampersand. Size is 6 bytes, and timeout I'm going to give it 1000. Right. Now we have read the 6 bytes of data from the particular register, which is nothing but the accelerometer register, and with this we are going to give the conversion. Okay, so how do you take the conversion? So let me going to assign this to the our structure variable. First one is the ax. Okay, this is equals to the ax value. Is how we will get the ax value? the upper bytes, the first byte is the upper byte, right? So take the read values array. So this is 0, but this 0 you need to left shift by 8 bits, and you must OR with the first byte. Okay, so this is how you will get the 16 bits of data. Okay, so just make sure that. And then similarly you need to do it for other other two, that is y and g direction. So this is ay, and this is az. Okay, and you need to give this as a 2, this as a 3, this as a 4, and this as a 5. Okay, this is how you can initialize the MPU6050, and you can read the data from the corresponding registers. Okay, so save the code. Now what I'm going to do is I'm going to call these functions here. Okay, first I'm going to initialize the MPU6050 initialization, and I'm going to pass the handle here. Okay, similarly I'm going to write the function here, MPU60 read accelerometer. The first parameter is ampersand, and the structure. So the structure again you need to declare here. So I'm going to declare a structure value here, or maybe somewhere here. So what is the structure? So this is the structure, and give MPU 6050 struct underscore t. Any name you can give, that's not a problem. Okay, so take this value, and then of course you need to pass it with ampersand. Okay, and let's give a delay of maybe 500 milliseconds. So that's all. Okay, so we have initialized the MPU6050, and also we have read the accelerometer data, and then we have given a 500 millisecond delay to observe the data. Okay, so first what we are going to do is we will upload this code into the board and see whether we are getting the MPU6050 accelerometer values or not. Okay, so just click on this project, and then click on hammer icon to compile the project. So we got 8 errors here. Okay, redefinition of errors. Okay, I'm sorry. Okay, let me remove these things. So I don't know how it happened. Okay, good to have some errors. Okay, and also you can do one thing here. You can convert this to typecast it to underscore t, since it is a 16-bit data. Okay, save it. Click on the project again click on hammer icon to compile the project. Hopefully we'll not see any errors this time. Yes. Okay, and so click on this debug icon to go to the debugger, and make sure you select the ST-Link GDB server. Click on OK. Okay, so what I'm going to do is I'll go to the live expressions. Okay, I'm going to add the structure variable. Okay, this is the structure variable, right? Just copy here and put it here, enter. So we are going to see on the live. Of course, we haven't done anything with respect to this AX, AY, and AZ. Okay, first we will only see whether we are getting the raw values or not. Okay, so just upload the code by clicking this resume button, and of course, indeed we are receiving some values here. You can see. Okay, and you can observe if I turn right, the X value is increasing, the positive X. If I turn left, the minus values are getting, and if I give the forward, Y values are increasing, and if I go minus Y direction, you see the Y values are increasing with respect to the negative direction. Okay,